All right, everyone. Round two, finding limits without using a graph. Again, this kind of has 2 points. The first is limits help us analyze functions in a new way. Rather than talk about what's happening at a y-coordinate, we can talk about what's happening as we approach the y-coordinate, because sometimes that y value may not exist in the function. And it's going to help us with something called derivatives that we're going to get to very soon. And derivatives are a massive part of calculus. So limits right now may seem a little abstract, like not super useful, but you'll see when we get to the derivative why it's an essential part. And actually, when we get to the second semester, integrals, they're also important there. So finding limits without using a graph. We have to get to a point where I can give you a function and you can tell me what the limit as we approach that value is without even looking at the graph. I mean, we're going to have Desmos, so you can use it. But if I give you an example like this, we're going to kind of build this up. I'm going to show you some things you can do and then provide some steps for you. But let's say I gave you this function, f of x equals 3x squared plus 2. And I ask for the limit as x approaches 0 of this function. So you could graph it, and you could do it that way, but the point is to try not to graph it and instead be able to do this using either algebra strategies or your brain about what's going on in the function. I'm going to use my brain about what's going on in the function. This is a quadratic. There's nothing funny going on. There's no asymptotes, there's no jumps, there's no holes. So if that's the case, then I don't have to worry about any spots where the function has a funny thing happening. So that should mean it's just whatever the y value is at 0. So in other words, I should just be able to plug 0 in and get an output. And if that output is a value, that's what the limit is. That's what the function's approaching as x gets closer to 0. So I plug in 0, I get 2. And that's the answer. Easy peasy. When there's nothing funny happening in the graph, the limit is the y value. As I get closer and closer and closer to the x value 0, the quadratic is getting closer and closer and closer to that y value 2. I think it's doing something like this. Okay. So that's how a limit works when there's nothing funny going on. Step up the difficulty a little bit. Say I gave you this function, 3 over x plus 5. And I ask for the limit as x approaches 0 in this function. Okay, so based on our rational functions, we know something is funny going on in this. This is a rational function. This has an asymptote, a vertical asymptote somewhere. And if you remember how to find it, it's when you set the denominator equal to 0. So that means there's a vertical asymptote at -5. Well, that's not 0. Is anything funny going on in the graph at 0 in this function? No. Again, I can just plug 0 straight in. How nice. And I plug it in, and I get 3/5. And that's it. That's the value. If I were to graph it, it would be 0.6. So we would see it in Desmos. I'm not going to do it right now just for the sake of time. You can try it if you don't believe me. But this method I just used on these both was called direct substitution. And direct substitution is always your go-to first move. So I would try direct substitution first, and if you get a value, that's the answer. So and it's not a jump, by the way. If it was a jump, you'd have to be a little more careful, but that only happens in piecewise functions. So direct substitution is a great strategy of plugging straight in. So when does direct substitution start to fail? Well, I can give you that same problem with that function g, but let's now do the limit as x approaches -5. So you have the limit as x approaches -5. You can try direct substitution. Plug -5 into the function and see what happens. So you would get 3 over -5 plus 5, which is 3 over 0, which is not 0. That is undefined. That's my little arrow, by the way. I drew a little arrow there. This is an arrow. Undefined. Does that mean the limit is undefined? Not always. You have to be careful. It's not a hole. But in this function, is that a hole? No, nothing canceled out in this function. So it's not a hole, it's an asymptote. And we already learned in the last lesson that asymptotes, the limit does not exist. So in this problem, the limit is a DNE. At vertical asymptotes, there's no limit. It's only when you have a hole. So direct substitution did not work. In this one, I would say use the graph. And I know I said we're doing it without graphs, but when I say use the graph, I mean your knowledge of the graph. So in other words, you should know or start to get familiar with the fact that vertical asymptotes exist when the denominator is 0 and that term did not cancel out. And so that's a helpful strategy. Use your knowledge of what the graph looks like. If you know there's a vertical asymptote, you know the limit does not exist. Okay, but then we start to get into the more interesting examples. Something like this. I want to start with this one. Okay, so you could try direct substitution. I think it's always good, and for reasons later, once we learn more calculus, we're actually going to come back to limits and learn some really cool ways to solve limits using calculus strategies. But I think you should always try direct substitution. So we're going to try direct substitution. Try direct substitution. Here we go. So plug it into the top, you get 0. Plug it into the bottom, you get 0. That's undefined. Here's my pet peeve. As soon as students see undefined, they think, oh, the function does not exist or the limit does not exist. That's not true. Okay, you cannot just say, oh, I got 0 over 0, it does not exist. You have to go through the other steps of trying to figure out maybe it's a hole, maybe it's a removable discontinuity. Maybe you can remove the problem from this function. And in this case, we're going to use some of our algebraic strategies. So we're going to use algebra strategy 1. Algebra strategy number 1, called factor and cancel, or I'll just say factor. Just like when we're doing rational functions, you should try to factor and cancel things because, hey, maybe it's a hole. And I already told you limits exist at holes. So we plug in 5, or so, we factor the top, difference of squares, which is why I had you reviewing some basic factoring. And look what happened. The terms canceled out. So now we're really doing this problem instead. Now you can do direct substitution. So now directly substitute. And when you plug it in, you get 10. And that is the limit. If you graph it, you can do it on your own because I don't want to take up too much time in this video. But if you graph the original function, you would see that there's a hole at 5 with the y value that looks like it's 10. So there'd be that spot hole at the coordinate 5, 10, and it looks like you're approaching that value from both sides. All right, so that's our first algebra strategy. What is our second algebra strategy? Well, that would be, and I'm going to give you a really bizarre one, if I gave you a problem that looked like this. This one is going to come into play when we start learning more of our algebra tricks. All right. Okay. Weird. There's a radical and a -2 and an x. This is a bizarre problem. It's been designed to help us with something later. So don't worry about the weird nature of this function. Instead, try to figure out the limit. So you can try direct substitution by plugging straight in. And I'm going to save you some time on the math. You get 0 over 0, which means who knows what's going on. In other words, do not just say it's undefined, that there could be more going on. So instead, you're going to have to use an algebra strategy. So use algebra strat number 2. Multiply by the conjugate. So I'm going to call this my conjugate strategy. Some of you saw this with me last year when we needed to rationalize. So this is the strategy on this one. I'll move this over a little bit. Going back to the problem. I'm going to rewrite it right here so we have lots of room to work. Anytime you see a radical, and you may want to write this in your notes, anytime you see a radical in the problem, minus another term or plus another term, you can use a strategy called multiply by the conjugate. We'll practice this a little bit because it involves a little bit of careful algebra. You're going to see why it works in a second, but first let's talk about, are we allowed to do this? Yeah, I mean, we're multiplying by 1. When you have a fraction where the top and the bottom are the same, that's really just multiplying by 1. So we're multiplying. So what do we get when we multiply? Well, you have to do the whole area model or double distributing or FOIL, whatever you want to call it. I typically say FOIL because FOIL in my mind implies this procedure. So it's double distributing, I guess, is another way. So you're going to multiply this term times the front one. Well, the radicals cancel. You are left with 4 plus x. The reason we do this conjugate strategy is when you multiply the front times the back, you get 2 root 4 plus x. When you do the inside, you get negative 2 root 4 plus x. They cancel out, and you are left with just minus 4. Okay, you can take some time there. You may have to go back and do that one for yourself because that's some algebra that you may have to dust off a little bit. And we'll practice some of that in the performance task. And then you multiply x times this. I'm actually going to keep it separate. So a lot of times you're going to hear me say, don't distribute the non-conjugate terms. Let's just keep them separate. All right, so this looks weird, but look what happened. The top, all the radicals are gone. That should always happen. The radicals should be gone when you do this correctly. So I'll come right there. Look what we have in the top. We have 4 plus x minus 4. It's all adding and subtracting. There's no term out here, so we don't have to worry about the parentheses anymore. And how nice, the 4 and the minus 4 cancel. All we have left up top is an x. So in this case, the x and the x cancel, and you are left with 1 over square root of 4 plus x plus 2. So in other words, you have removed the discontinuity from the problem. If you just graphed this function, the one in green I wrote down here, it would look exactly the same as the original. The difference would be the original has a hole at 0, whereas this one, I think now you can plug in 0 and get an actual answer. So now you can go through that whole part where we can directly substitute. When we try plugging it in and direct substituting, we get 1 over square root of 4, which is 2 plus 2 is 1/4. That's the limit. That means there was a hole in the problem. So if I go to Desmos, and I'm actually going to graph this one for you guys. I want to graph the original problem just so we can always tie it back to graphs, because a big part of this class, I'm going fast, I know, is using graphs to kind of confirm what you're doing. So we have this function. It was the square root of 4 plus x minus 2 divided by x. So if you look, it's a really funny function. It's pretty flat. It has a slight curve to it. All I care about is what's happening at 0. And if you look, if we go right to 0, we had it. It was undefined, which means there's a hole there. But if you look what's happening from both sides, as I come from this side, what value am I approaching? I'm getting closer and closer and closer to 0.25. If I zoom in and keep zooming 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 in, it looks like I'm getting closer and closer to 0.25 from the left. Looks like I'm getting closer and closer to 0.25 from the right. Even though as soon as you get there, bam, there's no value. I don't care about that with limits. What I care about is what value am I approaching, almost like what would you get if there happened to be a nice filled in chunk there. And that happens to be what we just found algebraically, 1/4. Okay, so those are our two major strategies I'm going to stop with for now. We're going to practice factor and cancel holes, and we're going to practice this multiply by the conjugate holes. For the sake of time this year, I'm not going to do the third type with you right now. We may come back, but it's the one that's easy to make mistakes on, and where it does not play a major role. You're just going to have to trust me with something later. Maybe I'll introduce it one day if we have time. But these are the major two, because these two are going to be super useful for what we're going to be doing when we get to derivatives. So let's back up, summarize real quick. Oh, that was cool. I didn't need to do that. Interesting. Okay, so finding limits without a graph. We started with direct substitution. That works when nothing funny is happening. In this one, something was funny. It was happening at -5, but not at 0. So we were able to plug in 0. In this one, we tried plugging -5 and got DNE, but we had to use our knowledge of the graph. There was an asymptote, so the limit does not exist. In this one, we tried direct substitution. Did not work, which means a lot of students say undefined. It's not undefined. You need to do more strategies. It may be something like a hole is going on, and it was. There was a hole in this function. The answer was 10. Same thing with this one. You plug in 0, you get 0 over 0, which was undefined, but it does not mean the limit does not exist. It could be a hole. And when we did this fun conjugate strategy, where the conjugate just means multiplying by the opposite sign, and we're going to practice these in the homework and performance task, you should get rid of the problem. That happens every time. and you're left with just your value that you can get by direct substitution. Okay. So we'll practice some of these on the homework and the performance task, and then we'll learn about left-hand limits and right-hand limits. We already kind of started talking about those. And then limits as we approach infinity. That means as x gets closer and closer to infinity, what is y approaching? Otherwise known as end behavior. So that'll be the next lesson, left and right-hand limits and end behavior. But the lesson for today was intro to limits and your algebra strategies. All right, and that's where we will stop.